Hello guys, this is Y, and today I'm going to do a video on BCD to binary conversion, but with logic gates. In the last video, I have do a binary to BCD conversion. It is the same thing and it uses the algorithm of shift and add tree, also known as a double algorithm. And in this video, I'm going to reverse that, and in reverse of that operation, you can convert binary coded decimal back to binary values again. And I'm also going through with how do you build the logic gate, and it is in a very similar fashion with the last video. So if you want to know more about the basics and the working principles of this algorithm, you can refer to that video. And let's go ahead and start this. So before today's content, we actually have the dabble, which looks like this. You can also know it as the shift and add tree. It revolves around two operations, shift and add tree to the values of it. So you want to shift your values to the left. Every single shift to the left one bit, and it may cross into other columns as shown below. This is the binary values column, this is the ones column, and this is the tens column. And as you know that binary coded decimal, they are coded in 4 bits of binary values, each representing a single digit in the decimals. So every time you shift here, you compare the ones in this column, and you see if this value is bigger than 5. If it is indeed bigger or equal than 5, you add 3 to it. So you can see this is 7. Then you add 3 to it and it becomes 10 in binaries. And then only you shift. And this is the basic working principle of the shift and add tree algorithm. So how do you do it in reverse is that you want to reverse the whole process. You want to start writing your values in the spaces here. Then at the end, all of your values will be in the binaries column and you will get your binary value. So let us go ahead and do it with an example first by hand before we start building the actual circuit. Alright, now we're going to go through this example, 243 in decimals. We know that if it is binary coded, you just change the digits to binary values, right? And then you try to do the shift and add tree in reverse. So what you need to reverse is that you need to realize that in the last step of the shift and add tree algorithm, the last step must be a shift movement. So shift movement is used initial. So what do I mean by this is that the first step you must do is to do a shift movement first. And the first thing you write down this number 243 BCD in the columns. You want to do the shift first before you do any subtract-free operations. So in reverse, you shift to the right instead to the left, and you subtract 3 instead of add 3. So this is what this means to be reverse. And then what is the condition is going to be is that whenever you encounter a number of value 8 or bigger, you do the subtract 3. And this is indirect project of the values of 5 or bigger, you add 3. So now if it's 8 or bigger, you subtract 3. So you can see there's a shift movement here, and it's the exactly same thing, just reversed. So you want to do subtract 3 if value is bigger or equal to 8. Alright, so 243, we have 3 columns. So you just write down your values here. Alright, so first step, you want to shift it. So you can see this value, it goes into the binary column already, right? So this is what you want to take note of. Let's mark it at 1. No, let's just mark it at A first. And we'll go through why I marked that later. It will be, the reason will be discussed when we are doing the circuits, when we are building it. And then only after the first shift, you start to test the condition of whether you should subtract 3. Alright, so this value is 1, this value is 2, this value is 1, so no subtract 3 happens. So you shift again. Alright, so now you have this 9. So 9 is bigger than 8, so you subtract 3 becomes 6. All the other bits just stay the same, and then you shift again. Alright, so there are no values to be subtracted here, so you shift again. And you have here 8, so you should subtract 3 for it to become 5. And then you shift it again. And you have here 8 plus 2 is 10. 10 you subtract 3, it will equal to 7. So 7 is this. So if it's just 0 in front, you don't need to write it anymore. It doesn't mean anything. It doesn't carry any values, so you can just ignore it. And now if you have 7 already, so now you shift. And you can see that this value will never be bigger or equal to 8, no matter how you shift it, right? So you can just take this value as your final answer. And this, in binaries, is equal to 243 in decimals. Alright, back to what we have discussed. So here you have the full operation of converting 243 in binary coded decimal to binary values. And here you have the binary values. And this is the rules you want to stick to in the procedure. And just remember the first ever step is to shift. Alright, so now we have done it by hand, and the next we are going to have a Carnot map, and then we are going to have our sum of product expressions, and then we are going to build the logic chip of this testing condition, and finally we want to build the circuit with reference to how the table works. Right, let's go through one by one. To build a Carnot map to let the operation cycle through, let's say you want to move to the next step, you want to test it again. After the shift, you want to test it again. You must have a input and output condition, right? So your input condition is that when you are testing the number, let's say you have 1010, which represents 10. So if you input that to the chip, what the chip is going to do is that it tests if it's bigger than 8. And if it is bigger than 8, bigger or equal than 8, it will subtract 3 to that value. So what you want is that from 0 until 7, it stays the same. It has the same outputs. And from 8 and onwards, the values is actually subtracted by 3, as you can see here. See? These values are all subtracted by 3, and they are still represented in the binary values form. So it's a very simple truth table, and from that you can build Carnot maps, and you can see the labels here, A1 to A4 and S1 to S4, and you can see the labels here as well. You just mark them down, write your own expressions, you mark them down, and you do it for all 4 outputs here, and you will get 4 sum of product expressions in total. You can see they are computed here. If you are still a newbie in digital logics, I recommend you to do this by hand every step, because the more hassle you've gone through, the more familiar you are with stuff, and the faster you can understand new concepts, and the more easier you can apply your knowledge to building logic circuits. If you are already familiar with how a Carnot map works, you can just go to the web and use a Carnot map calculator, any calculator that can do the job for you, because doing this by hand is just tiring and it wastes a lot of brain power. And now after we got the Carnot map and the sum of product expression done, we have to build the chip. And the chip is just a collection of these expressions. And so what the chip is going to look like is, so you have A1 to A4 labeled. So you want to leave it in the 0 states, and you have them connected to AND gates and OR gates, and you label these outputs or according to the sum of product expressions. Alright, so now you want to build the circuit using these chips, and the first step we do is shift. So the least significant bit will not go through any tests, and you can see this. So the first thing you do is shift. Alright, and then you only start to test them. So what you do is that you test them here, you test them here, and you test them here, you test them here. And remember that each chip, it must has 4 inputs, right? But you only have 3 numbers here. So you want to manually add a logic level 0 here. And this logic level 0, it is not going to change. It just stays 0 throughout the whole operation. Okay, so after the test, it should go to whatever values you want. If it's bigger or equal than 8, it will alter the values. If it's not, it will not alter the value. And then you want to shift it again. Right? So now you have 2 values not being tested. And then you have your second levels of chips, testing this one, this one. This one you don't need to test anymore, because what is the biggest value representable by 2 binary digits? It is 0011, right? And this biggest value is 3, and 3 will never encounter the condition where if it is bigger or equal than 8. So actually you don't need any more chips here, as well as here you don't need chips here. It is because 3 values, the biggest value is going to have is 7, and 7 doesn't need to be subtracted by 3. So now you want to shift it again. So if these are zeros, you can actually just cut them off. So in the process of building the circuit, you have to be aware of little details like this. So converting case-specific values is going to have specific circuits, but if you are in generally converting a 8-bit or 16-bit or 32-bit, you want to expect the maximum value possible, so you want to cover all the values. So if you are building it for a general purpose, then you need this case here as well as here, because who knows, the values will be 1111 here, right? Alright, so move on. You just shift and you add these chips. So in a circuit, if you have inputs like this, so the first input, it doesn't go through any of the tests, so it just straight to the results. And the first chip is going to cover 4 of these inputs, like so, and you have another chip covering here. So what you can see here is that this is actually representing this, the test case at the ones place. So this is the ones test, and this is the tens test. And moving on, you have something like this. So you move to the right, move to the left, sorry. So this bit here, it now goes to the results. It is only tested once. So now you move here, and this, the output of the tens will go to the input of this ones. So you can see what this happened is that this value here, it goes here and is tested at the ones columns. So what this means is that you build it like this, it is actually just this operation here, right here. So now you have the tens. 1, 2, 3, 4. Now this will be another logic level 0 here. Alright, so depend on your case. Let's say you have built to the third level, and this one here is straight to the bottom. 1, 2, 3, 1, 2, 3, 4. And if you have put a chip here, it is going to have 1, 2, 3 and another 0, logic level 0 here, right? But what happens here is that, you see, these original values here, when it reaches here, it's only 2 places here. So when it's only 2 places here, you don't actually need this anymore. So you can just go ahead and don't put this chip for efficiencies and for the circuit overall power consumptions if you're actually building a circuit out of it. And so you just go through all the way until you have tested all of these original inputting bits. And so the circuit, it goes like this. Alright, for a deeper understanding, we should go through 3 and 4 here. So the most significant bit, of the leftmost digit, it goes through the most tests. Let's say you have this number, you convert it into a binary coded decimal. This bit here does not go through any test at all. This bit here goes through the most tests in total. So it goes through three tests at the tens thousands place. Case dependent, it can be only 1 or 2 depending on the value of this. But if you are building it to test any number you input, then you want to put it through at least 3 tests in the tens thousands place. And maximum of 3 tests, of course. Because after 3 shiftings, there will not be any value left in the 10,000s place here. And you have a full 4 tests at the other places. So you can see this bit has the most number of tests gone through. So visually, this bit, it will go through the most number of the condition chips. Alright, so now you want to add zeros to the empty inputs of those chips. Because binary coded decimals inputs, they are in the multiples of 4s. You have either 4, 8, 12, 16, 20, 24, 28, 32 of those inputs. Because every single digit from decimals, it will result in 4 digits of binaries. This is why. But the LSB, the least significant bit, is not tested. And so it will be shifted by 1 column. And you can see that the leftmost chip there will have 1 empty input. And so you must connect a logic level 0 to it. Because no input does not mean it is logic level 0. To go through in detail, some of the logic gates, they are implemented with transistors, right? So if you have a NOT gate here, this is the power input, this is the ground, this is your signal input, and this is your signal output. And the NOT gate in real life, it actually has 4 pins instead of just what we learned for 1 input and 1 output. and those 4 pins, it includes power and ground. And so if the input is high, it means the resistance here is low, and the power will go to the ground. Almost all the power will go to the ground, and the voltage at the out terminal is low. So if it is high, this is low, but there is still electrical current, right? So if you don't have any input at all, it does not represent logical level 0. No, it represents no power at all. So if there are no power at all here, you get the maximum, all of the power will go to the output terminal. So it might result in a faulty signal, because in a gate, actually, it has its thresholds. Let's say the thresholds are set in 0 to 1 volts for logic level 0, and 3 to 4 volts for logic level 1. So if you have 0, totally no input here, all the power goes through here, and you will have all the power, so you have a peak signal. So what the computer interpret this? How does it interpret this? It will be thrown into a confused state. The computer does not know how to interpret if the voltage is at its peak. So this condition is different for every manufacturer. It depends on how the manufacturer set the threshold for their chips. And another reason it can go wrong is that if you have a AND gate, I don't know exactly how, but it looks something like this. If you have the AND gate, and if you have 2 inputs, this is ground, this is power, and this is output. Something like this, very similar. I don't remember exactly how it looks like. So if you have a input that is entirely not connected, and you have this input working correctly, so what this happens is that no matter this input is 0 or 1, it does not have any meaning at all, because if this is 0, it does not let any power through. Either this is 1 or 0, the power goes through out will always be the same, right? So you don't leave a input of any gate to be unconnected. You want to at least connect them to a logic level 0. In the simulation programs, if you leave one of the inputs to be not connected, let's say this, it will just give you outputs, but in real life, it might have glitches like this. It might result in false outputs, because in real life, things are way more complicated, and these conditions, they are not considered in some of the simulation softwares. So this is one thing you want to look out for, and just some extra knowledge. Alright, so since we have gotten all the details done, and let's just go ahead and build the circuit. Right, let's put a label. So what we're doing here is a 2-digit BCD to binary conversion. And if we have 2 digits of BCDs, that means a total of 8 inputs, right? So it's due to the nature of this chip that has a inputs closely packed together, I will have to stack the inputs here as well. So be careful when you are dragging the inputs here. You don't want to accidentally drag it to the side to connect 2 inputs. So just be careful. Alright, so you have 8 here, and you know this bit doesn't go through any of the tests. And you want to connect them like this. So if you can't see them clearly, let me just magnify that. Alright. This chip represents the comparison at the 1's place. This chip represents the comparison at the 10's place. And now you want to add a special logic level 0 here. Then you want another layer of chips, and this bit is going straight to the output. And you want a logic level 0 here. And now you can see in the third level of chips, no matter how big the original number is, let's say it is 1111 here, till this step, if you put a tens testing chip here, what it's going to test is that it's going to test the most significant bit here, so you don't actually need this. So you can just proceed with layers, and you want to cover it, and that is basically all the chips you ever need for this. So just go ahead and make it tidy. Alright, so you have 8 outputs. So now you will have your answers in binaries from binary coded decimals. So let's go ahead and play with this a little bit. So 0110 represents states, right? And 0100 represents 4. So now we have 64 in value. So 64, when it goes through all of these chips, you can see here 64, because this represents 2 to the power of 0, right? So this represents 1, 2, 4, 8, 16, 32, 64. So you can just go ahead and play around. So this is 99. You can do the math and check if it is correct. 64 plus 32 plus 2 plus 1. Yeah, that's correct. Alright, so this is how you want to do the BCD to binary conversion, and it is especially useful if you want to build a, let's say, a calculator. So this is one of its applications. So if you want to build a calculator using only logic gates, you may want to let the user input their values in decimals. Then you convert the decimals so they are expressed in BCDs, and then you use this chip to convert it to the binary values. And if you are doing the addition, it's just using the half adder component and the full adder component. Depends on how you connect them. And you can just do the addition of two numbers. Let's say you have another number here, and you go through the same steps, right? And you go through this addition, and you have your results, but the results is in binary, right? So you want to convert them back into BCD, and through the BCD, you display them back into decimals. So this is a very simple flowchart of how a calculator involving BCD to binary and binary to BCD and to decimals. So we have tutorial on this already, and we have tutorial on this already, and we have in fact tutorial for this already for converting BCD signals to 7-segment displays, and the video is in the digital clocks video. The info is in this video. You can check it out if you are interested. And let's see if I can do the half adder and full adder tutorials next. And if you have any question or suggestions, you can leave it in the comments. I will try my best to help. And thank you for watching, and good luck in your studies. Thank you.